Yeah, I'm good.
All right.
Thank you.
All right, so we are starting a new section on rational functions and just some basic functions. Now, normally there are more basic functions than this, but we're going to leave off trig since we haven't done trig. And we're going to look at everything that's non-trig related, which you should be pretty good with, because all of these, you should know enough to be able to graph them. Okay, and you can see that I think there are, 13 of them? So there are 13 basic functions we're going to look at. Have you guys, I think this is one of the things Hummers left off last year. Do you remember talking about the basic functions and shifts and reflections? Okay, so it's going to be a little bit more of a learning curve than in past years, but my goal for you is not to be able to plot points on these graphs. I know that you can do that. I know that if I ask you to graph y equals x, or y equals root x, or y equals x cubed, that you can actually plug in things for x, figure out the y, and mark those points. I know you can do that. My goal is for you to be able to see an x cubed graph and know that it looks like kind of like this. I want you to be able to see a square root graph and know that it looks like this. All right? And I'm going to walk you through that, but the goal is to be able to do these quickly and rapidly. And not like it's going to be some speed test, but I want you to have a vision of them. If you see a absolute value graph, which you might already know that, it looks kind of like a V. All right, now that V could change if I shift it left or shift it up or reflect it, maybe even stretch it. Those are the things we're going to talk about once we run through these. But you need to be able to have a working knowledge of how to sketch these graphs quickly. Because where we're headed with this is, instead of me giving you, say, y equals root x, which we'll talk about in a second, what I'm going to be asking you to graph, not tomorrow on the quiz. Tomorrow's quiz will literally look just like this, but it will say quiz at the top. That's it. So it'll be this exact same sheet with maybe one small exception in that some of these graphs at the bottom, I could change that number, and you'll see what I'm talking about when I get there. It might not be a 2 squared or a 2 to the x or a log base 2. It could be a 5 squared or a 4 to the x or a log base 3. So those kind of things might change, but the way that you go about the graph is going to be the same. So this will be your quiz tomorrow. It'll be a 26-point quiz. I am really hoping to give you 26 out of 26 to help your grade. And most people have absolutely no problem doing that. Are you with me? And if there are mistakes, usually they're really small ones, and most people end up with 20 out of 26 would be the bottom end. Most people are like 24 to 26 and end up with a pretty decent grade. So take advantage of that. Make sure you can really sketch these well, but your quiz will look almost identical to this sheet, even in the same order. Okay, so real quickly, I want to run through these, but the goal is to be able to know what this looks like so that when I give you something like this, you'll be able to look at this and go, oh, that's a square root of x graph. The only difference is it's been shifted down 5 to the left 1. It's been stretched by a factor of 2, and it's been reflected over either the x or the y. In this case, when you this particular one will be reflected over the x. But we're going to go through all these little rules so that you'll know how to do that. And then if I know how to shift the function down, shift the function over, I can sketch that little square root function like I would here with those principles in mind, and I can get a really good sketch really quickly, but I have to know what we call the basic function. Some books call it the parent functions. These are the basic functions, but the parent would be this thing right here, not all this uglied up version. And you'll see that's not a big deal. In fact, you've done this a lot with parabolas. Like with parabolas, which is right here, right, y equals x squared. Haven't you done graphs that were like -2 x plus 1 squared plus 5? The only difference is your 5 was over here. You had it written like that, right? Right? And didn't you think through this a second? Didn't you have a vertex that was -1, 5? So if you think about it, you started at -1, up 5. That's kind of like shifting left 1 and going up 5. Those what those numbers tell you. And if you knew that, just like you did with parabolas, you could go left 1, up 5, and you knew that parabola, actually it was a negative, so you knew that parabola would be going down, reflected downward, and it had a little bit of a stretch, and you used the cheap trick. So those kind of things we're going to be doing with these, all of these graphs. But before we can do any of that, we got another parent graph. And listen, I'm not going to know if your brain freezes up on a test. I'm not going to know if you go, oh crap, I forgot what the 1/x² graph looks like. I think I'm just going to plot some points. I won't know that. It's just going to take you extra time. And the more time you spend on that, it's less time you have for something else. So let me just run you through these real quickly. And this is what your quiz will be. No shifts, no reflections, no stretches, even though we'll do that a little bit today. All right. But the idea is, do you know what these basic functions look like? Now, first thing, on number 6, does yours look like this double absolute value, or does yours look like this on it?
Double absolute value.
It looks just like a double absolute value? Okay, that's a glitch right there in this. I don't know why it does that when it prints, because this is the PDF of it, and the PDF looks like that, but it should look like this. So put a little top that goes in on each of these, and that's actually called the greatest integer function. And you guys, again, I hate that you haven't seen that. We actually had a problem earlier in the year, and it asked you to graph the greatest integer function from -3 to 3, and it actually gave an example of a problem like this, but I don't know that anybody asked me about it, or certainly wasn't on a test, but anyway. So let's just walk through real quickly. What does y = x look like? Yeah, it's just a line, right? This is a linear function. This is the most basic of basic linear functions. It has a 0 x-intercept. The slope is 1, so you're just rising 1 and running 1. And you need to make sure when you graph these that you go all the way out, right? Don't get sloppy and do this, where it doesn't actually follow the slope. Make sure that you're keeping with the points consistently until it exits the graph. And I'm looking for it to exit the graph, okay? On your quiz tomorrow, if you don't do that and you just go to the right 3 and the left 3, I'm not going to give you your full credit on that.
So do we not keep drawing like arrows at the end?
You can if you want. That part doesn't matter. All right, y = x². Now, you probably already know that's a parabola, right? And since it's a +1, it's a +1 parabola. But the key to graphing parabolas is really understanding about 5 of the points. And a lot of times you can't even get 5 of them in. You probably only get 3 of them in. Okay, but on this one, because the a value is so small, you can. But again, if you think about what's going on, I am squaring the x value that I plug in, right? So if I plug in an x value of 1, I'm squaring it to get y. So 1, 1. If I plug in an x value of 2, I'm squaring it to get my y, which gives me a 4. If I plug in a 3, I'm squaring it to get 9. And the same thing's true if I plug in a -1 or a -2, right? If I plug in a -1, I'm squaring it to get 1. A -2, I'm squaring it to get 4. And of course, if I plug a 0, I'm squaring 0, but it stays 0. Those are the 5 points I want to see. Now, do all those 5 points show up on the graph if I were to put some a value in there like 4? No. Now what's happening? I plug in a 1. I'm squaring it to get 1 times 4. So that 4 would stretch what should have gone up 1. Now it's going up 4 times that. And right here at 2, if that was a 4x², when I plug a 2 in, what do I get? So instead of going up 4 there, I'm going up 4 times what I would have gone up, which would be up 16, which is clearly not going to show up. But I don't have a 4 there. Those are my 4 points. I'm going to come in here, and as clearly as I can, I'm going to sketch that problem. And these are all the basic functions, or the parent functions. Y = x³. Now, same kind of thing, except one thing. When I plug in negatives and I cube them, they don't turn to positives, do they? So as I'm heading to the right, these graphs are going up. As I'm heading to the left, the part's going down. Kind of looks like John Travolta from Saturday Night Fever, if you even know what I'm talking about. Whatever. So if I'm plotting the points, I really can't plot too many here. You saw here, when I squared 2, I got 4. That's plottable, isn't it? But here, when I plug a 2 in, when I cube it, I get 8. That's off my graph. So here's the thing on it. Most people get in their head, oh, well, you can only plot 3 points most of the time. True, unless maybe the graph was a lot bigger. So the points I'm concerned about are 0, 0, 1, 1, and -1, -1. But I'm also concerned on your graph to see if you really understand what the cube's doing. So somebody tell me why this is a bad graph here.
Needs to go up more.
It really needs to go up more quickly, because I know if I plug a 2 in, what would I get? But according to this, if I plug a 2 in, I'm getting 3.5. If I plug a -2, I'm getting -3. That's just not right, is it? So if I plug a 2 in, I really should be up here. Now that's off the grid right there. So what do I do to kind of account for that? When I'm sketching this thing, I just got to make sure that I haven't gone that far. Are y'all with me? So you should not be, when you look at your graph, you should go, wait a minute, could 2.8 still be attained? Yes. Right here, same thing here. I am not yet there at -2, -8. So I'm looking for that when I sketch the graph. But the 3 points that I really need you to go through are those 3 right there. And you don't have to make them all big, but you do need to go through them. Anything I have marked as a big point, you need to be going through those values. All right, what about this absolute value of x? Absolute value of x, I'm erasing all these. Absolute value of x is essentially doing what to any x value you plug in there? It's making it positive. So if I plug a positive 1, I'm getting a 1, or a 2, I'm getting a 2. It really looks like the line right here, doesn't it? Even a 0. But if I plug in a -1, the y ends up being +1. A -2, the y ends up being +2. So this really ends up looking like a line with a negative slope when you're heading left, and a line with a positive slope when you're heading right. And I don't know if you remember this, but the actual definition, do you remember the first week we were in school? I don't even want to remember the first week we were in school. But the first week we did the definition of absolute value. We had all these problems with absolute value in there. And what did I always say about it? Sometimes it's positive and you leave it alone, and sometimes it's negative, you got to change the signs. So literally what this means is sometimes it's a positive value, well, I leave it alone. That means y equals x. There's your y equals x. And sometimes that's a negative number, so to make it positive, you have to negate it. And look, there's your y equal -x right there. And it goes on to say this. It's going to be x when x is positive. It's going to be -x when x is negative. And technically, you could put the 0 on either one. But anyway, that's what the graph looks like. So just make sure, again, that you're following the slope of 1 there, slope of -1 there. All right, square root function. You learned this was a semi-parabola. You may not remember that, but whenever you see something that had that square root, you squared both sides in the last test. Oh, you got x equals y squared. That's like an x minus 0 equals a 1, y minus 0 squared. Do you see how that looks like a parabola? Except it's heading to the right, right? And which part do you keep? Do you keep both of them? No, only where y is positive. So this ends up looking like a half of a parabola going to the right with the top half. You don't have to memorize that. Think to yourself, what are the easiest points to plug in there that I will be able to take the square root of? 1, square root of 1, that works great. That gives me a 1. What else? 4, square root of 4 gives me 2. There's a great point, 4, 2.
0.
0, square root of 0 gives me 0. And I'd love to plug in 9, square root of 9 gives me 3, square root of 16 gives me 4, but most likely I'm only going to get 3 points in there, possibly 4. And then I can kind of sketch this. And when I sketch it, you can see there's half of my parabola, the top half. But we just call that the square root function. It just kind of hooks off to the right unless it's been reflected somehow. Now this other one, when I told you about this one, this should have, and it will on your tests and stuff like that, it should have these little bars on the top that kind of just go in. It's called the greatest integer function. All right, and the greatest integer function is another name for it, is a floor function. So a floor function, and there's also called and by the way, a floor function could also be written like this. It could be written like with just that. And while we're at it, I'll just mention a ceiling function, and I'll tell you what these are. A ceiling function can be written like, let me get rid of that. It can be written like this as well. Every now and then you'll see that at the Stavy or some math tournament, and it'll say evaluate, and you're like, what the heck does that symbol mean? Now, a floor function says this essentially. It's like your grade's worst nightmare. It says round everything down. Everything. If it's got a decimal, throw it away. Even if you get, say your test score is 89.9, and you're like, sweet, I got an A. Nope, got an 89. I just round the crud out of it. Not even correct rounding. It means if you have not gotten to that integer, too bad. We're going to go just to the greatest integer you've got to, and that's it. Now, once you hit that integer, you're safe. Okay, you're on base, all right? So once you hit 3, great. But 3.1 rounds down, 3.3 rounds down, 3.9 rounds down. Now, if it was a ceiling function, which is not this, greatest integer functions are floor functions like that. A ceiling function is what I do with your grades. No matter what you have, I round it up. You get a 75.1, 76. 99.3, 100. I round up on everything. Well, actually, sometimes I don't round to 100. I'm sorry. Sometimes I don't round when you're over 100. So like when you get like 101.5 or whatever, which a couple of y'all got, I'm like, you know what? They're already so high, whatever. But most of the time, I round everything up. Are you with me? That would be a ceiling function. It's like push it to the ceiling, the other one's push it to the floor. Well, think about what that does on a graph. Integers, when I plug an integer in, it's already an integer. So there's no rounding that needs to happen. So values like 0 stay 0. Values like 1 stay 1. 2 stays 2. 3 stays 3. All the way through. Same thing with negatives. -1 is -1. -2 is -2. So you start out looking like, oh, this is just a line. Not so fast. Now what happens is, think about what happens, and I'll start with 2. 2 is 2, great. But what's 2.1? Still 2. 2.2, still 2. 2.4, still 2. 2.6, still 2. So all of these 2 points are just going to stay 2. 2.9, still 2. But what happens the second you hit 3? Jumps to 3. So I've got to put something at the end of that to show, at the end of this little platform, which we call a step, at the end of that I put an open circle to show that I jumped up. So think about 3 now. 3 is fine, 3, 3. But what about 3.1? Still 3. 3.3, still 3. 3.5, still 3. 3.7, still 3. 3.99, still 3. 4, jumps to 4. And you've got another open circle. Well, I could do this all day long, but what do you start seeing? Little steps to the right with an open circle at the end. And you can just do, so what I like to do is just mark the dots where a line would be, and then just make a little step to the right, put an open circle at the end of it. Now, you're not going to get asked to graph this except on my test, but you will get asked to understand this. And this is what, like, maybe there's a Vestavia problem a little while ago that said something like this. The greatest integer function of pi plus the greatest integer function of e plus the greatest integer function of 7.4 plus the greatest integer function of -6.8. And it's really testing your knowledge of the greatest integer function and of stuff like this. So what's the greatest integer function of pi? 3. Rounds it down to 3. What's the greatest integer function of e? It's 2. Because e actually, and you need to go ahead and start getting this in your brain, e is a number like pi that is irrational. It definitely means something. You see it all the time in physics, calculus, logarithms. We saw it a little bit in the logarithm. Definitely in exponential growth and decay. We use it all the time in calculus with exponential growth, with Newton's law of cooling, all kinds of things like that. It's just a number that shows up so much that they gave it a name, but it's roughly 2.7-ish, kind of like pi is 3.14-ish. So if the greatest integer function of 2.7-ish was there, it would be 2. All right, and then you get to 7.4, which is 7, and here's what gets tricky for some. Negative 6.8, negative 7. Because you're rounding down, right? So rounding down is kind of like rounding left on the number line. Y'all with me? So if I'm at negative 6.8 and I'm trying to get to negative 6, I didn't really get there, did I? All right? So you're rounding down to a negative 7. So when you added all that up, you get a 5. Y'all seeing this? Okay, but that's how these work. And you can see it right here. Look, what happened at negative 1.5? What did I do? I ended up at what? Negative 2, rounded down. Negative 4.1 right here. Negative 4.1, where did I go? Oh, sorry, all the way. Where did I go to? Negative 5. So on all of these, I'm rounding down. So that's the greatest integer function. And then moving on, and by the way, a ceiling write those. All right, and I'm not going to use either of those on your test, so you don't have to know those. I'm just going to use this one. All right. Moving on to the last half, number 7, x to the 1/3. Do y'all know what a 1/3 power means? It's the cube root function. So fine, think of it as the cube root function. It'll be easier for you to process. So just like the square root, there are certain numbers in there that will probably make it easier for me to do, right? So what numbers are easily cube rooted? 8 is. The cube root of 8 is 2. So if I plugged an 8 in, I would get 2. Now I can't fit that on my graph, plug in an 8 and get a 2, but I like seeing it because like the x cubed function, it keeps me from going too high when I'm sketching it. What other number is easy to plug in there? 1, cube root of 1 is 1, so 1, 1, that's definitely a point I want. What else? 0, cube root of root is 0. Now, unlike the square root function, on the square root function, if I plug in negatives, what do I get? I get imaginaries when I plug in negatives on a square root. But do I get imaginaries on a cube root? No, in fact, I told you guys, if you ever see something like a cube root of negative 8, what do you do with the negative? You just take it out. It's not an I that comes out, it's a negative comes out. So if I ask you, hey, plug a negative 8 in there, and you just took the negative 8 out, the negative out, what do you end up with? Negative 2. So at negative 8, you're down here at negative 2. And at negative 1, where are you? Down at negative 1. So with those 5 points in mind, I can sketch this graph. But just don't go too high. That's why I like plugging in the 8, just like I did on the x cubed. So I just don't go too low or too high when I sketch it. You with me? All right, what do you think x to the 2/3 is? So it's the cube root of x squared? There's actually 2 ways you can think about it. I like not, like you could think about it as the cube root of x squared. I think to me, it's easier thinking about it as the cube root of x then squared. To me, it's easier to plug values in. So what values do you think will go in there? Cube root function. 1, 8, and 0 still seem logical, right? Because I'm cube rooting them. So let's think about it. If I plug a 0 in there, I get a 0. If I plug a 1 in there, cube root of 1 is 1. 1 squared is still 1. Starting to look a lot like the other one, right? If I plug an 8 in there, cube root of 8 is 2. But then when I square it, it changes. It becomes 4. So out here at 8, I'm actually much higher than before. So what that means is, unlike the cube root function, which is kind of skinny or really flat, this one has a little bit more elevation. So when you sketch it, you ought to be going just a little bit higher, but not too high. And that's, again, why I plot that extra point on there. Wait, though. What about negative values? Can I plug negatives in there?
Yeah.
You can always plug negatives in there, but wait, what happens when you square them at the end?
They become positive.
So this one, instead of being up here and down here like this, it's going to be up here and up here. All right, so think about it. If I plug a negative 1 in there and cube root it, I get negative 1. But when I square the negative 1, I get positive 1. When I plug a negative 8 in there and cube root it, I get negative 2. But when I square it, I get positive 4. So we call this the bird function. Kind of looks like a seagull, like when you're drawing seagulls at age 5 or whatever. Not like Kim Kardashian's kid, you know, who can do Monet-like pictures at age 7. Anyway, y'all with me? All right, y equals 1 over x. We call this the reciprocal function. But it really just looks, you'll see it in a second, it kind of looks like this. All right? And then the next one down here, the 1 over x squared graph, we call that the volcano function because it kind of looks like this. I say we, maybe Helmer's not called that. I don't know what the universe calls it. But this is a reciprocal function because essentially what it says is whatever you plug in for x, I'm going to take the reciprocal of it to get my y. And that's kind of what you're doing, right? Now, what values do you want to plug in there just to kind of get started? 1, if I plug a 1 in there, I get 1 over 1, which is 1. What happens if I plug a 2 in there? I get a half. So if I plug x is 2, I get a half. What about x is 3? Third, x is 4. Fourth, x is 5. Fifth. So what's happening as I move to the right?
One of those things that doesn't touch the line.
It's one of those things that doesn't touch the line. What do we call those when it doesn't touch the line, but it gets closer and closer and closer? Asymptotes, right? Or astropoles, whatever works for you. So I got an asymptote running like this. So what I do is I don't plot all of these. I don't. I plot this 1, 1, and then I just go, you know what? It's just following that curve down there. That makes it a lot easier on it. Now, just for the sake of showing more, what happens if I plug a 1/2 in for x? What's 1 divided by a half? 2. So if I think x is a half, I'm now up 2. What if I plug a 1/3 in for x? So in x is 1/3, I get a 3. X is 1/4, I get a 4. X is 1/5, I get a 5. What does it look like it's doing there? Another asymptote. So am I going to plot all those points? No, I don't see it. I'm just going to mark 1, 1, that one right there, and follow the asymptote. Now, what happens when you plug in a negative 1? You get a negative 1. Anybody got a guess on what's happening here? The exact same thing. It's following the asymptotes. So rather than go through the pain of plugging all those points, I'm just going to take this and I'm going to follow a little better than that. I'm going to follow this and just get closer and closer to that x and that y axis without going over it. But I am going to want those 2 points. If you come in here hot and sloppy like this and go, oh yeah, volcano graph, you're not showing me that you really understand it. This volcano graph looks like it's been shifted down 5. That would be like a 5 right there. And that part will be important to me, is seeing that you understand about, not shifted, but reflected, stretched more 5 that way, because you should be a -1, -1, not -1, -5. Are you with me? Yes, no? So make sure that you're hitting that point and then following the asymptote. And another way you could think about it is, can I plug a 0 in for x? It's undefined, right? So there's nothing that can exist at x. Can this fraction ever equal 0? No, because for a fraction to equal 0, what part has to be 0? The top, the numerator. And the numerator is 5. So neither the x cannot equal 0 and y cannot equal 0. And that's why you have asymptotes in both of those locations. Although we'll talk more about that with rational functions in this chapter as well. All right, last 4. And then hopefully we'll have a moment to talk about shifts and deflections and stuff. All right, number 10, 1 over x squared. Now the 1 over x graph and the 1 over x squared graph are similar, because this is really 1 over x then squared. So what do you think the 1 over x part does? The y equals 1 over x part still is undefined when x is 0, right? Can't hit there. This fraction can never equal 0. Asymptote there. So you still have the same 2 asymptotes. But what do you think the squared does? Keeps it from being negative. So basically, you're still going to have an arm that looks a lot like this, but this arm's not going to be down here. It's going to be up here. But again, I want you to show me you know about a couple points. So right here, think about it. What would happen if I plugged in 1? I get a 1, and if I plug in a negative 1, I also get a 1. You can see them both heading in the same direction. Now see if you can see the difference here. What happens when I plug a 2? I get a 1/4. How is that different than the 2 on the other one? So the other one I had 1/2. This time I have 1/4. So it looks like it's getting down to the asymptote a little quicker, isn't it? Y'all seeing that? Now it's not that noticeable, but, and I probably wouldn't count off if you didn't get that down there that quickly. Now, next question. What happens if I plug a 1/2 in there? Last time I plugged a 1/2, I was up 2. This time I plug a 1/2, what happens? Stay with me. I square the 1/2 and get a 4th. I divide by a 4th and get a 4. So before at a 1/2 I was here. Now I'm there. So what is actually happening here? It's almost like a stretch of the other graph, but what it means is I'm going up so quickly, I haven't gotten to the asymptote yet. So it kind of leaves a little bit of a kind of an opening at the top. Hence the volcano action. And by the way, if you do have an asymptote on your graph, I would strongly, in fact, you're going to see it anytime I shift or whatever, but when you have an asymptote, I strongly encourage you to mark those asymptotes with dotted lines when you have them. Now you're going to also see them with shifts and left and right and up and down. You're going to mark those shifts as well. But it's helpful those because it kind of gives you a vision of where you're approaching. All right, last couple. Anybody? I'm going to just make one up right here. Y equals 9 minus x squared. Does that look familiar at all to you from the conic sections test? It's a semi-something, isn't it? And if I squared both sides, I would end up getting y squared. That goes away. And then I'd add x squared to the other side. And what do you see? A circle with a radius of 3, right? Located at the origin. Now, the problem is it's not a circle because it wasn't that to start. But it's a circle whose y values are always positive. And if the y values are always positive, it's a semicircle. So you need to recognize this as the semicircle graph. And I will not write it as 2 squared. I'm just trying to illustrate that it's the radius squared. I'm going to give you something like 4 or 9 or 25 or whatever. So change yours to 25 just for fun, and let's look at that. So what that means to me is that is the semicircle graph. To the right 5, to the left 5, up 5, and maybe down 5, but no, not in this case, because y is always positive. So all I got to do is take those and do the best I can at drawing a circle and trying not to draw a triangle out of that. And by the way, unlike a something that sometimes we draw a semicircle with a bottom on it, there's no bottom on this, okay? It doesn't look like a lemon, just the curved part. And then number 12, what does that look like? What do we call those graphs? Where you have a number, number 12, a number with a variable up top. These are exponential curves. Exponential curves have the variable as the exponent. Curves that have the number as the exponent, the variable as the base, those are polynomials, like parabolas or whatever. But if the variable is the exponent and you have a number that's the base, those are exponential functions. Have you heard about exponential growth before? What grows exponentially, hopefully? Money in your investment account, right? In the bank, it's not growing that fast. It's the most pitiful interest rate in history these days. But yeah, if you're having it in the market, stock market's booming. I mean, just absolutely throwing down. I mean, in the last 4.5 years, I've doubled my money almost in the market, which has been glorious, especially when you have kids going through school. So that's been really great. In the bank, actually, 0.1%. I mean, it's just an absolute abysmal. But exponential growth is like population. Population typically grows exponentially over a long term, especially populations of larger populations, like of the United States or of the world. I mean, the population of Roanoke, Alabama, or something like that would probably not grow as exponentially as some, just because there's limited resource, limited stuff going on. Although it might grow some. And sometimes these small towns, not any disrespect to Roanoke, but some small towns start really stinking. I mean, not smelling stinking, but they're just terrible. Like New Brockton, Alabama. It's a dead town. My grandmother-in-law and her husband grew up in this town, and it's starting to thrive and get better. And then when they built the highway down to the beach, they just skipped New Brockton. So when they skipped New Brockton, everybody's like, well, there's really no access point. The highway didn't go through there. There was nobody visiting, nobody coming through to get gas, nobody stopping for food. Everything just folded up. And now you just got a bunch of old people living there that happen to own farmland, and they just happen to reside in this bad, terrible little town. Anyway, whatever. I used to have to go there for like every Christmas and every event. It was just, there's like one place to eat, and it's terrible. Anyway, whatever. All right, so y equals 2 to the x. But to graph it, it's easy to plot points, right? What happens if I plug a 0 in there? What's 2 to the 0? So if I plug a 0, I get a 1. If I plug a 1 in there, I get a 2. If I plug a 2 in there, I get a 4. And you're probably not even going to get that many points on this graph. Because think about it, if that was a 3, what would have happened? A 0 is still a 1. A 1 is a 3, but now a 2 is a 9 off the curve. So unless my base is 2, you're probably only going to get a couple points, right, that are going to fit on you. Now, your base is 2, so I was able to get 3. But you can see that the graph is going up to the right, isn't it? Now, those are all the 3 I need to see from you. As long as you remember that exponential functions do this. Think, what happens when I plug a -1 in there? What's a 2 to the -1? So at -1, I'm up a half, okay? Again, you don't have to do this if you just remember what I'm showing you. What happens when I plug a -2 in there? 2 to the -2 is what? It's 1 over 2 squared, which is a fourth. So at -2, I'm up a fourth. What do you think happens at -3? 1/8. -4. 1/16. What is happening to this graph? There's an asymptote. So all I need to see from you on this is sketch the 2 most obvious points. The ones when you plug in a 0, plug in a 1. And if you can get lucky, plug in a 2. And then just connect those. And then just follow your asymptote. You don't need to do all those points to the left. It's a waste of time. Now, the logarithm. Do you remember about logarithms? A little bit?
Yes.
Now, what were logarithms inverses of? Exponential functions. But everything's just flipped. All the x's and y's. So if everything's flipped, if exponentials have horizontal asymptotes, then logarithms have vertical. Well, guys, again, you don't need to plug a zillion points in for these. All I need is 2. And if you have 2 points and an asymptote, you can sketch the curve okay. Same thing over here, although because it's base 2, I'm going to be able to slip 3 in there. Now, do you remember some of the basic rules for logs? Like this. What is log base 2 of 2? 1. And the rule was if those 2 numbers match, you can use their exponents. So if I plug a 2 in, I get a 1. That's a point. Plug a 2 in, go up 1. Now, what did you learn about every logarithm when I log the number 1? You get a 0. There's another point. Plug in a 1, I get a 0. Now, for this particular one, I can plug in one more point because it fits. What would happen if I plugged in a 4, which is a 2 squared? Y'all remember that? Because of the rule says, if I rewrite that 4 as 2 squared, 2 over 1. So if I plug a 4 in, I get 2. Well, I can fit one more in, but listen, I'm not going to be able to do that if it's log base 3 or log base 5. There won't be enough room. So again, I'm looking for two easy points, which is that and that. And you know not to plug a 2 in if there's a 3 there, right? If there's a 3 there, plug a 3 in, right? So if you plug the matching number in, you get a 1. If you plug 1 in, you get a 0. There's 2 points. And what do these points do? They follow themselves out, and then what? Follow the asymptote. So just dive down. Just like over here, you slid out to the left. And those are your 13 basic functions. And I wanted way more time than this. This kind of hurt because you guys didn't learn that. Last year I would have been able to fly through this because you'd already learned it. So I think this is what we're going to do. We are just going to, you're going to go home and study. You're going to learn these basic functions. And tomorrow we're just going to try to squeeze everything in as we move through the week. But if we can't, we'll just bump stuff back a bit. I'm truly not worried about it. Did y'all get an assignment sheet? No. So right now, here's your assignment sheet, but you are probably not going to be able to do these shifts, reflections, stretches. But I'm just going to hand it anyway. It's on the fly here. Yeah, we haven't even talked about the homework, so I don't know that you're able to do it. Not do it? No, I'm just giving this to you because I'm just probably going to help that.
She got, and she said they got 78, and then she said the grade was already that we used on close, and then changed it to a 9.
So again, guys, don't worry about the homework tonight. We'll pick up with that tomorrow. But study for the quiz. The quiz is tomorrow.
I know back then.
All right, Dave.
So, yeah. Oh, really? Yeah. And I'm checking out for sure. And it was my friend.
One more time.